All right, class. um, Hope you guys are doing well. Um, I just had an acai bowl for lunch. It was really good because it's so hot today, and so I was able to cool off a bit. Um, have something to show you, which are my new Crocs. I love them. I haven't been wearing socks because I have my Crocs now. They're very comfortable. This is like the closest shirt I have to matching with it. I don't really care. It doesn't match. Whatever. Um, I'll show you what else I got. I also got I had talked about the axe layer, and so I got myself a throwing axe. So, look out. Um, all right, so it looks like I have some questions. Let me take a look at it. I'm still a bit confused about the daily items. Are we turning them in this Friday or next Friday? Also, since it's instead of a quiz, does each person have to? Okay. Um, so you're going to do the April 20th quiz as normal. You're going to submit that by Friday. Next week, if you look at the 427 quiz, all it says is submit your workbook pages. So instead of sending me a quiz next week, you're going to send me this week's review problems. Okay? You can send them in a group of 4. That's fine. Each person doesn't have to individually type up their solutions or write it up or whatever. Okay? So as far as the page numbers from yesterday, those you guys were doing pages 230 to 233 in the workbook yesterday. So if you have more questions, ask them in the live chat, and I'll address it at the end of the lesson. But otherwise, I consider the matter closed. Okay. So I'm doing. By the way, the AP test is 3 weeks from today. So I'm going to be just continuing to do the workbooks problems up until the AP exam, which is Thursday, 3 weeks from today, and hopefully you guys will be well prepared. Okay. All right. So looking at the problem, the scenario is balloons 1 and 2 hang from strings connected to the same point in the ceiling. Both balloons are given the same sign net charge, but not necessarily the same magnitude of charge. The balloons hang in equilibrium as shown in the diagram. The grid in the background may be useful in estimating the angles or slopes of the strings. Okay. Each dot below represents one of the balloons. Draw a free body diagram showing and labeling the forces exerted on each balloon while they hang in equilibrium. Okay, so if we look at each balloon is connected to a rope. Each balloon is connected to, so ropes exert a tension. Each balloon has a weight force. And then there's the electrical repulsion. Okay. So I want to draw 3 arrows for each. So I'll have a weight force. I'll have a weight force going down maybe I'll have the weight force going down 4 units. Okay. We can see that the slope of this, it goes 1, 2, 3, 4 down and 4 across. So this one is going to be, let's see, over 4, up 4, something like this. Like that. So that's the tension. And then we also have the electrical repulsion like this. Okay? So that's supposed to be a straight line. One thing to notice is that the net force is 0. How do I know that the net force is 0? I can see that the downward force is 4 units long, and I can see that this arrow, the diagonal arrow from tension, goes up 4 units. See how that works? So the upward force is the same as the downward force. Similarly, the leftward force, which is 4 units long, is the same as the rightward force, which is also 4 units long. Okay? As far as the other balloon, you're going to see the same thing. It's just you're going to have a different slope for the tension. So we'll have an electrical repulsion that is 4 units long, like that. Why did I have to draw the electrical repulsion as 4 units long? Is because the forces are equal and opposite. Okay? And then I have the tension force, which has to go over 4 and up 8. So let me draw the tension force. 1, 2, 3, 4, 5, 6, 8. So something kind of like this. Okay. The reason I did that is because this force goes over 4. Okay, so it's going to cancel out the horizontal electrical repulsion. And then we also have the weight force that goes down like this. So those are your forces. Let me see if I can draw a head on this arrow, like that. And you'd want to label those. Okay, mark an answer to each of the following questions. Which balloon carries greater charge? I would say that there is not enough information. Why is that? Because all we know is that these are equal and opposite forces. You know, you could have, it doesn't matter if one has a charge of 2 and the other one has a charge of 1. We calculate KQ1, Q2 over R squared. It's the same thing as if we do it the other way around. So there's no way of knowing which one has more charge. Which one has greater mass? I would say balloon 2 has greater mass. Why is that? It's because basically the rope is more vertical for balloon 2, which means it's heavier. The heavier it is, the more it's going to want to just go straight down. Okay? So balloon 2 is heavier. Another way you can see that is if you even just look at my diagram, the fact that the 2 electrical forces are equal and opposite, okay, means that this force had to go over to the left 4 units. This force had to go over to the left 4 units. Okay. And since it's a different slope, because it went over the left 4 units, it had to go up 8 units, which means that the weight force on the balloon 2 had to go down 8 units. So it's a longer weight force arrow. Okay. The string supporting which balloon exerts a stronger tension force? Again, we can see based on the free body diagram that this arrow, that the arrow for balloon 2 corresponding to tension is quite a bit longer. So we want to say balloon 2. Oops. Balloon 2. So the reason that they're, keep in mind that these are 2 different ropes attached to each balloon, so they can each have a different tension. Okay? So it says in a clear paragraph length response to justify your answers. I just did that, but I will still, since I'm a nice guy, I'll type it out. Why not? Okay. So I would say something along the lines of F equals K Q1 Q2 over R squared. The force is the same, or I would say, so the force is the same if Q1 and Q2 are swapped. So there's no way of knowing which has more charge. Then for the next part, I would say balloon 2's rope is more vertical, which indicates more mass. And then for part 3, I would say because balloon 2 is more massive, the rope has to support more mass, therefore more tension. Something like that. Okay? So, wow, that's pretty straightforward. All right, we have a new scenario. Let me check the questions really fast. Theo asks, so we don't need to print out the pages. We can write our work. Yeah, if you want to type your answers into a PDF document and then send it that way, you can. If you want to print out the pages and write on them, you can. Or if you want to literally just print out line paper or just use line paper and write out your answers, that's fine. I don't care. One thing that's important is for these workbook pages, I'm not grading them based on correctness, just completeness, okay? So I'm just going to check it off if it's complete. So this quiz for this week is the last graded quiz until after the AP exam. All right. For the next scenario, it says, consider a charged box and a charged sphere somewhere in space far from other objects. So somewhere in space far from other objects, that's telling you basically that there's no gravity, okay? The box is very massive so that it can be assumed to remain at rest. but the sphere is light and able to freely move. 4 cases below show different combinations of signs of charge on the box and the sphere, as well as the initial direction of the sphere's velocity. Assume that all cases have the same initial speed of the sphere and that the initial distance from sphere to box, magnitude of charge on the... Okay, blah, blah, blah. In which of the cases above is the speed increasing at the moment shown? So, in order for the... I'm just going to type it out. I'll type it out. In order for the speed to increase, the force on the sphere has to be pointing in the same direction as the velocity of the sphere. Okay? So if you push something along its direction of motion, it's going to speed up. If you push against the direction of motion, it's going to slow down. So let's look at each of these cases. If we look at case A, the force is a repulsive force because they're both positive charges. So the force is going to be in this direction, which is the same direction as the velocity. Okay? So this one is going to be increasing the velocity. Here we have 2 negatives, and so the force is repulsive. We can see the velocity is to the left, but the force is to the right. So this one is going to be slowing down, so that one's out. Here we have an attractive force, so because it's opposite charges, but the velocity is to the right. So the force and the velocity are in opposite directions. That's going to be slowing down. That one's out. And then here we have an attractive force because it's opposite charges, and the velocity is going to the left, so that's going to speed up. So the answers are case A and case D. Oops. All right. In which of the cases is the magnitude of the acceleration increasing at the moment shown? All right, so I'll type in my answer to this one. Oops. Type in my answer. So I would say F equals ma. So if the acceleration, so if the force is increasing, so is the acceleration. Okay, and then I would say the electrical force is F equals K QQ over R squared, which means the force is getting bigger when the charges get closer together. So the ones that have an increasing acceleration are the ones where the charges are getting closer together. So let's evaluate it. Here the charges are getting farther apart at the moment shown, so that one's out. Here the charges, in case B, the charges are getting closer together, so that one is Good. In case C, the charges are getting farther apart, so the force is getting weaker. So that one is out. And then in case D, they're getting closer together. So the force is getting bigger in size, and so the acceleration is increasing. So the answer would be B and D. That. Oh gosh, here we have another argumentation with Carlos and Dominique. Carlos and Dominique are asked to rank the net force exerted on the sphere in each of the cases. In part C, consider all forces acting on the sphere. Carlos incorrectly says that all four net forces are equal. Dominique correctly says that FC equals FD, which is greater than FA equals FB. All right. All right. So what I would say is for Carlos, so Carlos is incorrect. But why did Carlos think what he thought? He would say, well, F equals K Q1 Q2 over R squared. And in all cases, okay, in all cases, the charges are the same and the distances are the same. So the forces should be the same. But, what is wrong with Carlos's argument? Well, there's a second force that is very, very weak, but it is present, and that is gravity, okay? And so if we look at gravity is going to provide an attractive force in all of these cases, okay? So what are the cases where gravity is helping out the electrical force? That would be cases C and D, because cases C and D have electrical attraction in addition to gravitational attraction, so that those two forces are combining to make an even bigger force. If we look at cases A and B, the force is repulsive, but gravity is attractive, so those two forces are canceling each other out, which makes a smaller net force. So C and D are going to have bigger net forces. So I will say gravity, etc. All right, is there anything else? Oh, that's it. All right, lovely. So it looks like that's our workbook problems for today. And thank you to the 15 of you that watched. I appreciate it very much, your participation. And I hope you guys have a really nice afternoon. And tomorrow we'll be back with some more workbook problems. I actually like these workbook problems. I think they're kind of fun. So I don't know about you guys, but they're not outrageously difficult, and they kind of like test your understanding pretty well. So I enjoy doing them. All right, thank you very much, and have a good afternoon.